Thank you. They'll continue what we started discussing yesterday. Start by a short review of what we did yesterday. And so here, what we did yesterday was a first principle derivation, starting from Feynman diagram of a dual description of the Fishnet model at strong coupling. Correspondingly, the dual description was completely classical. We reproduce, for example, the spectrum of the 4-point function, but solving classical equation for a set of particles on the light cone in embedding space. What we're going to do today is take this model and quantize it. And see what happened at finite coupling. And again, just to zoom out, the aim of all of that is to have some general playground for ADS-CFT, that we can see the general structure, and then we hope that the same structure persists for n equal to 4 or other holographic theories. In particular, we'll have an explicit holographic map between the degrees of freedom on the boundary and this fish chain degrees of freedom. I'll promote it to the quantum level today. And what we'll discuss tomorrow is how to use this more in understand how to compute, for example, correlation function, how to use integrability techniques. And the idea there will be that we first compute in this simplified model and then replace the blocks by the known blocks in n equal to 4 and hopefully compute exactly correlation functions there. So just to review what we did yesterday. So the new thing about what doing yesterday was a bit think about the wave function dual to local operators in radial quantization in the CFT. More precisely, we did was considering this Fishnet model, which consists of two complex scalars, and only one complex interaction here. You should think about the Hooft coupling psi here, general as a complex parameter. There is no reason with this action to take it real. It's actually more useful to think about, to take it a bit off the real axis. The operator that we consider was the operator in the so-called U1 sector, that were operators that only charge under phi1 rotation and not phi2 rotation. And it's a small change of what we did to include all operators. And they correspond to some state on the S on the sphere, which one way to parameterize it is to probe the operator with J conjugate scalars. So a basis for the wave function was this 2J correlation function. Think about the 2J correlation function if we do some point splitting here to regulate the operator. And the bottom line was to think about the graph building operator, this B that add another layer to these Feynman diagrams. And we saw that physical space correspond to stationary wave functions under the graph building operator. So, for example, for J equal to 2, this was the exact finite coupling spectrum, and we reproduce it by eventually by taking this psi to be very, very large at strong coupling. No, S is spin. Here, this is for J equal to 2. Of the operator here, of the state. Okay, so we are looking on operator which is primary operator of some dimension delta, and it can have some spin S. Yes. So specifically for J equal to 2, this was just a 3-point function between two scalars and operator, which is completely fixed by conformal symmetry. And by just applying to it this conformal operator, just in that case, just star triangle identity, and you get the spectrum directly. Now, the dual model that we got yesterday was a model of J particles on the light cone in embedding space. This is embedding space. The projective light cone in 6 dimensions, and the Lagrangian, we get, importantly, have 1 over h bar playing the role of the Hooft coupling, square root of the Hooft coupling, with J canonical kinetic terms, and some complicated nonlinear interaction in between them. Okay. And these etas were just a Lagrange multiplier that imposed that we stay on the light cone. And it came with constraints, Virasoro type constraint. One tells us that the interaction and the kinetic terms are of the same order, like a varial theorem, and the other tells us that the Lagrangian density is independent of the site index. And I called it curly L. These were the two Virasoro constraints. And yesterday, we fixed the gauge. It was written in this way. The action is one additional gauge symmetry that we have not fixed yesterday, which was combination of overall rescaling of all the coordinates and of time. And yesterday, we fixed the gauge where the sum of the etas was equal to 1. And this was the reason to introduce this big R. It was the Lagrange multiplier imposed in this constraint. Today, we find it more convenient to change and fix the gauge where the Lagrangian density is just a constant independent of time. This is the most standard actually gauge fixing. The only reason to do that was to try to introduce ADS radius in that case. We will see today how ADS radius comes about, but it will be slightly different. It was called in Fishnet because the diagrams is a form of a fishnet. The original by Zamological, I think, back then. And here we call it a fish chain, just between the two. So again, what are we going to do? This is all classical. This is only when psi is very, very large. We have to solve the equation of motion subject to the constraint at a classical level. Okay? This is the analog of a string action in ADS. And the problem if you quantize in the string action in ADS is that the interaction is very nonlinear. So it's very tough. It's not straightforward like quantizing string in flat space. And the same play the role by this interaction here, which is, look, highly nonlinear. Okay, so here what we're going to do, we're going to pass from the classical world to the quantum world for this fish chain, having in mind that in n equal to 4, with this nonlinearity, we can only do quasi-classical. So here is the problem. I just changed it back from Lagrangian to Hamiltonian by the canonical transformation, replacing the x dot square by p square and the sign. And the constraint that we have is that we are on the light cone, that the Lagrangian density was constant, and I set it to 1, and we have to impose the Hamiltonian constraint, meaning that it's translating some non-physical time on the world line. I want to quantize the system. So what it means to quantize such a system, just following the textbook direct way of quantizing quantum mechanics with constraints. Okay? So to start with, we will introduce Poisson brackets. We'll then try to improve the Hamiltonian by adding it to the constraint, such that by itself, it will commute with all the constraints, so that we take Poisson bracket with the Hamiltonian, we don't generate new constraints. Just a finite set of constraints. It will turn out that some of the constraints are first class and some of the constraints are second class. When you have a second class constraint, you have to worry that when you do commutation relation, you stay on the constraint subsystem. And this is exactly the difference between Poisson bracket and Dirac bracket. You have to improve the bracket such that after you take commutation relation, you're going back to the constraint subsurface. And this is what the Dirac brackets are. This will change Poisson bracket to Dirac bracket, and then quantization is just changing Dirac bracket to commutations. And 1 over h bar is psi, is a parameter. After that, we will study what is the Hilbert space, what is the space of wave function that satisfy the constraint, and finally, we will impose the Hamiltonian one and read what is the spectrum. So this is the plan for today. Now, even that, I want to start with a different problem, which is much simpler, that you can open Wikipedia and the solution in a slightly different way, but is derived there. It's just the quantization of a point particle, non-relativistic, just a free-point particle on the sphere. It turned out to be very much analogous to our problem. So free-point particle on the sphere, we have Hamiltonian, that is just a free Hamiltonian, p squared over 2m. We want to study what is the spectrum of this quantum mechanical problem. Okay. Now the constraint, one constraint is that we are on the sphere. So x squared is equal to 1. It will be the analog of our constraint p squared equal to 1, but here it's x. And there is a so constraint that follow from it, like taking the time derivative of that, I tell you that x dot p is 0. So the momentum is conjugate to x because we are on the sphere. Now let's try to go through these steps and would apply them step by step to this problem. After that, we'll go back to our problem and it will be straightforward. So first we introduce a Poisson bracket in the standard way, and our two canonical variables are just the position and momentum on the sphere. Now I want to improve the Hamiltonian in such a way that it will commute with the constraint. Note that there is a very nice way to do it. Let's Q be the generators of rotation of the sphere. Okay? So it's a d by d matrix. If you take the trace of q squared, you see that what you get here is p squared up to terms that are proportional to the constraint. X is set to 1, and this one set to 0. Okay? So instead of the original Hamiltonian, we can just consider the Hamiltonian, which is trace q squared. You take, this would be the improved Hamiltonian, trace q squared over 4m, which automatically commute with all the constraints because they are covariant. Hamiltonian just made of the generator of rotations, and all the constraints are invariant and rotations. Because the Poisson bracket between, yes, if you take the Poisson bracket between H and C1, you get C2. Exactly. H generates time translation. You take the time derivative of this, you get exactly. Next, we want to close the system of constraints. Take the commutation relation, the Poisson bracket between them. And if you take the Poisson bracket between these two constraints, you automatically get out a factor of 2, back x squared. If you need the Poisson bracket here is non-zero, it's 2, meaning that these two constraints are second class, not first class constraints. Okay? It means that we have to improve the Poisson bracket to put us back on the constraint system, which is subtracting this difference, which is the commutation relation with our two second class constraints. And this Dirac bracket now have the property that if you take any function of x and p and take its Dirac bracket with the constraint, you get 0. They put us back on the space of constraint. I think I had a picture for that, yes. So I'll go to it in a second. Quantize now, we have to take the Dirac bracket and replace them with commutators. Nice thing about it is that first x's, the Dirac commute, so that they become commuting operators, meaning that we can now parameterize the Hilbert space as a wave function that are eigenfunction of x, eigenstate of positions. That's what we do. So we work in position space. However, the p's, they denote Dirac commute with themselves because of the improvement. Okay? And this relation here, and also commutation with the x's, was improved by this term that put us back on the space of constraint. Here k, I wrote it here, k is just the derivative with respect to x. K take us here, and replacing the Poisson bracket by the Dirac bracket, just the improvement that puts us back on the sphere. K is just a conjugate to x. Okay, derivative with IH bar times derivative with respect to x. It means that we can represent now this P, even this commutation relation, as the conjugate to x plus an improvement term, exactly that put us back on the sphere. And the improvement term, we can easily convince ourselves that it must be proportional to x to satisfy the constraint, and the coefficient is by itself k times x. Because P have to satisfy the constraint that if you multiply it by x, you get 0. Right? And this C here, so here we have a product of two operators. So now there is an order in ambiguity in the quantization. And this C is just a constant representing this order ambiguity. So for now, I leave it unfixed. Again? We will, yes. We'll fix it in a second, but it's amount to pick in the C2, the second constraint. Also there is an ordering ambiguity. Yeah. So what is, I'm going to study the Hilbert space. So we have the first constraint that classically tells us that x squared equal to 0. This is trivially promoted into an operator statement. And you can check that you can systematically impose it on the Hilbert space. No problem here. Importantly, just tell us that you can now parameterize the wave function as a delta function of x squared minus 1 times the wave function that just live on the sphere. This is what it tells us. Not that this wave function by itself is not normalizable in the original space. There's only this delta function. This just follow from the constraint that we have to live on the sphere. Important because we get something very similar for the Fishnet leg. Next, we have to impose the constraint that x dot p is equal to 0. And here again, we have to face an ordering ambiguity because these now two operators that do not commute. And choosing the ordering of these two in the constraint exactly corresponding to choosing the C factor before. And you can choose either ordering, it will not affect the physics. So here I chose the order x times p, p times x. And the reason I chose this ordering is that it corresponds to setting C that was before just to 0. For this choice of ordering for the second constraint, this is the relation between p and k, which was minus IH bar dx. Finally, we have the standard norm on the sphere. So now let's go and study the spectrum. The Hamiltonian started his life as p squared over 2m, but we improve it by replacing it by trace of q squared such that it will commute with all the constraints. And now q just become an operator, the operator that generates rotation on the sphere. And this is nothing but the quadratic Casimir on the sphere. So it's given uniquely in terms of the representation under rotation. It's parameterized by the spin s and the dimension of space-time. So we've solved the model. This is the spectrum. What are the wave functions? The wave function, just we have to choose some polarization vector and take the product to the power s. This will be like the highest weight compared to that specific choice of polarization vector, and then you can rotate it. Yes. Nothing more than that. So now I want to go from this problem that we solved to our problem, which is the fish chain. What is the difference? You see, here we have the constraint x squared equal to 1, and it's analog to the constraint p squared equal to 1 that we have for the fish chain from our gauge fixing that the Lagrangian density was constant. The constraints of C2 fix this form, basically. That is automatically, if you plug this one here, it's automatically satisfied. If I now represent the Hilbert space by representing this operator. Okay, so now we're going to do exactly the same for our fish chain. The analog of the constraint C1 that we are on the sphere, now become that we are in the sphere but in momentum space. We now have an extra constraint that we are on the light cone, so x squared equal to 1. And similarly, because we have x squared equal to 1, or p squared equal, x squared equal to 0, or p squared equal to 1, there is a constraint that follows from them that x dot p is also equal to 0. And in addition, we're just studying the spectrum now of the Hamiltonian. The Hamiltonian itself become now a constraint. We have these two more constraints in addition to these two that are just analog of these two that were here. We're just now to follow exactly the same steps. Yes. gauge. Okay. The Hamiltonian constraint came from time reparametrization, which was the gauge symmetry originally. This is a first-class constraint. Yeah, we'll study all the constraints. Some of them will be first class, some of them will be second class. Yes. So we started the same way, Poisson bracket, and then improve the Hamiltonian. So Poisson bracket, just in the standard way, with between now X and P in embedding space. The Hamiltonian, improving the Hamiltonian now to be, again, very similar. If one study now, not just a trace of Q in one side, but taking the ordered product of Q square of all sides, and take the trace of that, one find that we get exactly our Hamiltonian up to higher order terms that are set to 0 by the constraints. So this way of writing the Hamiltonian is much nicer because you automatically commute with all the constraints, because these are just generators of rotations, and all the constraints are local and are scalars under rotations. Our improved Hamiltonian will be just trace of order Q squares for all the sites. Oh, because these are ordered, right? So when I take Q square at one side, I'm not taking this trace, it's a matrix. And then I multiply it with its neighbor, you get xi times xi plus 1. Okay? Which is exactly also determining the interaction. Yes. You multiply this by, so our constraint is h equal to 0. Multiply this part by this part to stand in front. Now I have we have the constraints also that tell us the Lagrangian density was constant. It was equal to, no, but this is not what I want to say here. No. It's straightforward. But yeah, let me postpone the answer. Okay. It's nothing like that. It's very straightforward. The way to think about it, maybe I'm not answering your question directly, but if you think back about the inverse of the graph building operator, the kinetic term was boxes, and the interaction term was 1 over xi plus 1 multiplied by all of them, without this factor that came out after integrating the eta variable. Sorry. Without integrating out the eta variable. If you multiply by it, then the constraint that b equal to 1, which is equivalent to this one, comes just the product of p's multiplied from the left by the product of xi plus 1. Again, I have to use the constraint that relate, in order to show that directly, I have to use the constraint that relate the interaction to x squared. But if you take the one, maybe more direct way to see it, you take the inverse of the graph building operator, minus 1. This was product of boxes, product of p squared, plus 1 over the product of the propagators. You take this and multiply by the product of propagators. It's become product of the propagators times product of p squared minus 1. Okay? And this was automatic. This is exactly what you get here by plugging this inside and opening the trace. Okay, so we'll use this Hamiltonian instead of this one, which are equivalent on the constraint subspace. And we automatically commute with all the constraints. Next, we have now to close the system of constraints. We can compute the correlation function between this constraint. Cx was telling us that we are on the light cone, that x were equal to 0. Cp was telling us that p squared is written here. This was equal to 1, and Ci was the one that was obtained by taking time derivative of each one of these and tell us that x is perpendicular to p. Okay? And because of this minus 1 here, we see that Cp and Cj are second class, while Cx is third class. And also the Hamiltonian is first class. This means that we have to improve our Poisson bracket into a Dirac bracket by putting these correction terms using Cp and Ci. Next, we are going to quantize by replacing the Dirac bracket by commutator. And as before the x's commute, it's now the p's that commute. If the p's commute, but I still want to work in position space, so I can still write the wave function in position space where these y's are just the coordinates that are conjugate to p. Okay? Let p equal to d to dy. So the fact that they commute means that I can write the wave function in p space or Fourier transform it to this y coordinate that are the position that is conjugate to p. Now, as before, the Dirac bracket between the x's and themselves and x's and the p have this improvement term. So let me use this y, that is according to that minus I h bar d to dp, to relate x to y. This is exactly the way we relate before p and k, that was d to dp. Now it's between in x's in terms of p, and you have this improvement term, which is proportional to y times p, and there is, again, an ordering ambiguity represented by this constant c. Exactly the same as we had before. Now let's realize what is the Hilbert space. Consider first the constraint that tells us that p squared is equal to 1. This constraint is just telling us that a box of the wave function is equal up to h bar to the wave function itself. This becomes a bit like a radial equation in embedding space. Here R is just the overall scale of y on embedding space. So y squared equals minus r squared. Okay? We are not necessarily on the light corner. Okay? We didn't pose any constraint like that. And C2, again, is the quadratic Casimir, but the local one. Trace of q squared at a given site. This is the definition of R. I should put here 3 lines. R squared is just the overall scale of y, the definition. I'm saying that this equation I can write like that. So in order to solve it, we have to know what is C2, what is the local C2 for the site. Yes, nothing else. This is just change of variables, indeed. Again? Psi, here. Oh, this is local constraint that we impose at each site. Yes. Yes, but this is about the Hamiltonian, which couples all the sites together. What we are talking now is just what is the evil space before imposing it. Okay, to given site. Okay. So indeed, this is just the radial dependence and the angular dependence is just the Casimir of rotation. quadratic Casimir in a given site. So in order to fix it, we have to know what it is. And the way I'll do it now is remember that the wave function originally came from a wave function that we used in the Fishnet model using J scalars. This wave function was originally the correlator of the operator with J conjugate scalars. This is the way we probe the operator. Therefore, when you act on it with the C2 at each individual point, just get the C2 of a scalar, which is -3. It's given by delta, in general, delta times d minus delta, which in our case, because delta equal to 1, C2 equal to -3. And I'll just replace the C2 by -3, and I completely can solve for the radial dependence of the wave function. And the solution turns out to be some Bessel function. And if you look very, very far, it's just a plane wave, which is the Fourier transform of the delta function we had before. But what will remain after factoring out this overall dependence is now a wave function in ADS. Okay? Because after we factor out R square, we remain with Z, where Z square equal -1. Parameterize R times the overall scale times the coordinate square is -1. Okay? So now, instead of being classical on the light cone, you see that at the quantum level, we're describing J quantum particles. Okay? They're like scalars with mass square in units of ADS equal to -3 in ADS. They're dual to the original scalars. Next, the second constraint was P dot x equal to 0. Again, the same story. We have here an ordering ambiguity. And if I pick the order in P times x, it corresponds to setting this C before to 0 and realizing the relation between the original x and the coordinate y, which is conjugate to P, in that form. Same way as before. Next, we have the first-class constraint that was x squared equal to 0, and you can just plug it in and see that this wiggle equal mean on the space of constraints. And you see that on the space of constraint, this x squared is just equal to -3 over xi squared. Since we have an ADS radius, which is quantum, order of h bar squared. So this would be, therefore, the quantum correction to this constraint. Okay? This constraint that classically just puts us on the light cone. At the quantum level, it puts us at ADS with a quantum radius. Okay? Stated basically by the mass of the scalar, or by the dimension of the scalars in the Fishnet model. Next, we want to study the spectrum of the model and just now promote this classical Hamiltonian into a quantum Hamiltonian. So how to promote the generator? This is clear. We are just promoting the coordinate into operators. And these are the generator that generate rotation at the quantum level. We now have to try to understand what is the quantum Hamiltonian. Let me, quantum Hamiltonian was trace of product of QI square. If we take, let me define, call like normal order Q square. It's the same as taking this Q as an operator, squaring it, but then improving it by two terms that make it first symmetric and second traceless. This one responsible for the trace, and this one responsible for making it symmetric. So I claim that at the quantum level, we should consider this Hamiltonian with these two quantum corrections that make Q square symmetric and traceless at the quantum level. So let's now test the model as we did before. What would be the simplest test? The simplest test would be to put one fish, one scalar. But naively, one scalar is trivial because this was symmetric and traceless. So if you take the trace of Q1 square, you got automatically 0. To make it still non-zero, we'll have to twist this model. twist the trace. I replace this trace of q squared by trace of q times some rotation matrix. For simplicity, we took here a rotation matrix that just rotate into orthogonal planes by the same angle. It looks naively as easy to break the rotation symmetry into these two planes, but actually it will have all rotation symmetry. This breaking is not seen at all at the level of damage. So now this Hamiltonian is non-trivial, and we can study the wave function. And again, the wave function, if we, it's a conformal operator, so if we pick it to have some spin and some dimension, we remain just with the function of the radial direction in ADS. And here rho is just the radial direction in global ADS. Okay, because we choose to diagonalize the time propagation in global ADS, which corresponds to radial quantization. Okay, so this is just embedding space in global radial and time motion. The rotations? Yes, but the point is that interaction now become between a point and the same point rotated. Now the difference between the point and the same point rotation is just depends on the overall length of the vector. So it doesn't break rotation symmetry at all. This is a special thing about j equal to 1. Even though this looks as if it breaks rotation, it does not break rotation. Break dilatation, you choose a frame, but you're not breaking any rotations. So now we have to impose the constraint. This was just the wave function at C2 is equal to -3 and the Hamiltonian constraint. Let's do that explicitly here. Here is the wave function and with some polarization vector, and rho again is the radial direction in ADS. We have here this single scalar interacting with itself with a twist. So first solving for this equation, it gives you an equation for the radial motion in ADS. And it's fixed, therefore, the radial dependence uniquely by the solution to this equation. You find that this equation has two independent solutions, as usual, and only one of them is regular in the bulk. Another one is singular at rho equal to 0. So this fixes for you the regularity in the bulk, fixes for you the solution uniquely. Next, we have to impose the Hamiltonian constraint, and just plug in this inside, you immediately get the spectrum amount to solving this equation in terms of delta as function of psi and the twist angle, and this is the spectrum we get. And tomorrow, it will be mainly about twisting. We'll see that this is indeed the correct spectrum of the twisted Fishnet model for j equal to 1, okay, at finite coupling. Let us go to the case that we considered before, which is j equal to 2. We have two scalars, and now they interact with each other. So now the wave function is a function of two coordinates on ADS, z1 and z2. So first, we have to impose the local constraint, equivalent to solving the bulk equation of motion for a scalar of mass m squared equal to -3. We get two massive scalars in ADS, and next we fix the global charges, as we did before at the classical level. This is dimension and spin. So one way, for example, just as a curiosity to compute the corresponding wave function is by a Witten diagram. It's kind of a simple one. If you put an operator on the boundary of ADS with some dimension delta and s, and probe it with two scalars in the bulk, there is a unique bulk interaction that can couple them. This is a single Witten diagram that gives you the wave function. In a second, I'll give a general way how to construct it. But it turns out that it's not even needed to compute it exactly. We can apply H and use the constraint to read directly the spectrum. And when we do that, we reproduce the finite coupling spectrum. Okay? But now, from the model in ADS. this was j equal to 1 and j equal to 2. Let me now go to general j and give a direct map between the boundary wave function and the bulk wave function. Yeah, graph building generator, yes. Yes, because this is a bit analog to this equation. When you act with the graph building operator on the wave function, which there was just a 3-point function, you get some function very similar to that. It has 4 terms, not 2, because j equal to 2, of delta and s. There's like something like delta minus s and delta plus s minus 2 times the shadows of this. And this was equal to psi squared. Now when you invert that, so psi squared just appear linearly in this equation. And when you invert it as delta, now as function of psi, this is how you get this relation. When studying the graph building operator was an exact. When we did a classical limit, we, of course, was blind to any such quantum corrections. It was just classical. Yeah, I got the same thing, but not doing any classical thing, but just diagonalizing the graph building operator. And diagonalizing it for j equal to 2 was trivial, because it was just acting on it. No. You want to take the graph building operator and act on it with a 3-point function. And this is just an integral, which is the star triangle identity, and you read the spectrum directly. Or act on it with a differential operator, which is the inverse of the graph building operator. You get it in one line in Mathematica. Now I want to give a proof of that for general J, basically. You see that the bulk wave function and the boundary wave function are very much related. So the wave function of the model was a function of J coordinates in ADS. And it satisfies this J local constraint. Let me now try to map the Hamiltonian, the quantum Hamiltonian here to the graph, to the inverse of the graph building operator directly. So we fix again the charges, and we have to impose this constraint. This was the quantum dual model for any J. So now I want to recall again that what we really were solving for in the terms of the CFT, we were looking for stationary wave function under the graph building operator. This now big psi, don't confuse it with the small psi. This was the CFT wave function in radial quantization. And the graph building operator was this complicated operator. But now I just rewrote the same operator in embedding coordinate. Okay? So the propagator here becomes just a scalar product, and the integration becomes integration over embedding space with a delta function that puts us on the light cone. Okay, so this is the definition of this D4. Now we note a very curious fact, that the inverse of this operator is nothing but the trace of the product of Q square. But now this Q square are the generator of conformal transformation acting directly in the CFT. If you compute this directly, it's exactly inversing this integral operator. We see this the same structure, only after getting it from the quantization, we went back and said it had to be so. Again? It will be a conformal Casimir if it was a trace in a single site. But now you multiply them ordered one after the other. only have to get in it for the quantization. You say it must be working like that already, the CFT. Then we went back and checking that it was indeed working like that. It's precisely that. Yes. Now, in order to lift it to the bulk, all we have to do is to integrate it against J bulk to boundary propagators for scalars, for scalars of mass -3 in the bulk. So this is automatically through the boundary wave function into the bulk wave function, and just by symmetry map the inverse of the graph building operator to the fish chain Hamiltonian up to a shift by 1. This basically proves the duality for any J. We finally a bit talk about the norm, because we were discussing it a bit yesterday. So in the CFT, there is a standard norm. Okay? If I'm computing two-wave functions and trying to read the norm of them, this is basically the two-point function in the CFT. In terms of this wave function of scalars, it's given by putting this operator. Maybe one way to think about it, suppose you have, in the free theory, you just have a scalars. If I act with a scale on two propagator with the box and integrate, I just get a single propagator, which is the two-point function in the free theory. And this is the general norm there. And we can now lift it to a norm in the bulk. Under the map between the boundary and the bulk wave function, the wave function in the bulk just becomes partly the action for J scalars of mass -3 in ADS. And both of these operators are self-adjoint with respect to this norm. Yeah, this is what we discussed yesterday, where unitarity is being violated. This is not violated by the norm, it's violated by some overall twist. One way to think about it maybe is from the worksheet, is that what we are twisting is the periodicity constraint on the worksheet. Instead of going back to the same point, we're going back to a different point on the sphere that is boosted with respect to it. So we're like twisting the level matching condition. This is what is responsible for making the spectrum not real. You may think about it a bit in some gauge as the Hamiltonian constraint. This is a bit a single constraint which is directly related to the level matching of the original string theory. Any questions before this is a bit a change? So far, I haven't used or discussed integrability at all, and yesterday we did not have time. So let me now just flash the basic ideas of how we see that the model is integrable, first at the classical level, and then at the quantum level. If you want to, there are two ways. One thing is the most physical way, which is introducing back the Hooft coupling of n equal to 4, which amount to, remember the interaction 1 over x, I dot xi plus 1, came out from integrating out a tensionless string between these string bits. We're trying to put back lambda, which will amount to integrating back in this string that will now start to see that it's really living in a finite ADS in terms of the original string scale. This is the way I would like to go. There is another way which is directly in this model, which is taking the large J limit. This doesn't work very much in the naive way because the interaction is singular where the 2 points collide. But there is a non-trivial way which amounts also to tuning the coupling to some critical point. And this was studied before purely from the integrability point of view by Benjamin Basson. No, you have to regulate the interaction that is singular when the 2 point collides. If you do it by hand, then you will get a good, it will look, if you by hand regulate the singularity, you get just string in ADS in conformal gauge with some constant contribution to the Virasoro constraint coming from the extension of the sphere, you can think about it. But this is naive. More questions? Yes. The classical model was in the light cone. The quantum lives in ADS. We had J quantum particles in ADS. So scalars of mass square equal -3, exactly dual to the original scalars of the Fishnet model. The scalar itself was a good operator in the Fishnet model. It cannot get any correction by itself, and these were just a dual to it. So, R square was up to a factor 1 over xi square. Yes. Yes, but yes. Yes, but it's not the tensionless I meant before, because there is also lambda of n equal to 4, not xi, which measure the radius of ADS in unit of the original string scale, which this one was set to 0. Yeah. There is a bits of the string that are stretched on the sphere, and even though the original tooth cavity was set to 0, they're still becoming not completely tensionless, because they are, at the same time, the amount that they stretch on the sphere was set to infinity. So their effective tension remained finite but quantum. Let me discuss a bit integrability without going into much detail, just the very basics. First, classical integrability. If we have a discrete model, what it means that it's integrable? It means that it's integrable, it means that we can construct two matrices that satisfy like the zero curvature condition. If I take L, some site I, and take its time derivative, it just get multiplied from the left and from the right. You think about by the connections, Vi and Vi minus 1. And this automatically tells you that if you now take the trace of J of these, it will be independent of time, because these will just cancel between the neighbors. In our case, we found that indeed there are two such operators. L is just made of Q square, Q, and a constant. Q here, it's a comment. Q here is just a parameter, free parameter. And the fact that these are independent of time, meaning that when you take this T and now expand it, say in Taylor series in U, you generate infinite many conserved charges. Because we have a finite system, not all of them will be independent, but they are enough to fix the solution uniquely. In our case, this J and V are just given by a combination of the generators, and this J, the J are defined in that way, commutator of the two x's divided by their product. And you can, for example, check that Q dot by the equation of motion is just proportional to the difference of two such J's, meaning that if I sum of Q's on all the sides, these will vanish, and the total charge is conserved. Okay? Yes, this is the definition of small j. And this is what stands here. This is what stands there basically in the equation of motion. If you know. So this is classical integrability. We have enough classical conserved charge to fix the solution classically for any j. What it means at the quantum level, we have to replace this L operator by, I think it's called Lux operator, for any site. Okay. Now, there is an important difference. Before, this L was made after generators. Okay, the generator acts on embedding space. There were 6 by 6 matrices. So transforming in the 6 of the conformal group of SO1, 5. There is a more fundamental object, which is the same thing, but now transforming in the 4 in the fundamental of the conformal group. Okay? And it's given again by just U times. So we now introduce, this is the physical space where the site K is. Introduce some auxiliary space. Both of them take now this one to be in the fundamental representation, which means in the 4 of the conformal group. And this lag combination is just a combination of the identity plus a tensor product of the generator acting on the physical times the same generator acting on the auxiliary space. Okay? So these are just 6-dimensional sigma metrics, which are 4 by 4 matrices, satisfy the same algebra as the Qs. Now, to prove integrability, one has also to construct, it's called the R matrix. R matrix is the same way as this one, but when these two lines are both in the auxiliary space. Okay? Or both in the 4, and this is just a linear combination of the identity and the permutations of the two spaces. And to prove quantum integrability means to prove what is called the RTT or RLL relation, which you can write it like that. This is what allows you to take chains of two such matrices and commute them. So here is one, and here is the other. We can use basically Young-Baxter with this R is this one, and these 2 points are this one to prove that they commute. And this is indeed satisfied if you plug here the generators and here the sigma matrices, which is explicitly that this integrability is satisfied at the quantum level. And this is the quantum transfer matrix that generate all the conserved charges in the 4. But what about the Hamiltonian? To go back to the Hamiltonian, it's important to go back to the 6 representation. Remember that classically, this L was in the 6, not in the 4. In order to get it, what we have to do is to multiply 2 representations into 4. This gives you the 6 and the 10, and then to project to the 6. At the quantum level, this is what is called fusion. You are multiplying tensor product of 2 of this L in the 4, and you project out to L in the 6, and you find that at the quantum level, this is L in the 6. Okay, you see that in the classical, it automatically reproduces what we had before. Okay? And to read the Hamiltonian, one just construct is the first conserved charges. In the 6th representation, one construct the transfer matrix, which is the product of this, and just set the spectral parameter to 0, and indeed, it reproduces our quantum Hamiltonian. So maybe the bottom line here is that when constructing here this quantum integrability, I haven't had to do anything special, just assuming that we have a chain of particles realizing the conformal group in the 6. Nothing more than that. And the rest just follow. Let me summarize. So we see that this fishnet yeah, I would have expected you to get the same thing. Yeah, but now 1 loop, 2 loop. Yeah, yes. The nice thing about here is we can use this iteration of the graph building to resum all loops. So let me discuss a bit future directions. One direction is to go out of this U1 sector that was just operator that charged under phi 1 but not phi 2. This is a very small modification of what I did and hopefully will appear soon. More interestingly, one would like to, so far we just described basically the single string Hilbert space, the propagation of a single discretized string in ADS. What we would want to do is now to include the string vertex, how it splits into 2. This is exactly captured by the 1/n correction in the Fishnet model. Second thing is that this model, because it's so simple, we understand it in the classical limit, it's an ideal background to start and study the integrability-based operation of variable for correlation function. This is what we plan to do, and then try to lift it to n equal to 4. For n equal to 4, we know the corresponding building blocks. So this is where we talked already a lot. We would like to turn on back the original Hooft coupling. And for a similar problem, which is the Cast-Wilson loop, for example, this was done before for the first order. And it gives you some correction to the evolution operator. In that case, it will give you some correction to the graph building operator. So one can do it in principle in a systematic expansion. There are other fishnets. In particular, there are one that is supersymmetric, the one corresponds to the beta deformations. It will be interesting to generalize this model there, and there we expect also to have fermions in the bulk correspondingly. There are analogs in 3D and 6D for ABGM model. We expect a similar thing. And this is what I also discussed a bit yesterday. You can study the same type of diagram in any dimensions. But there is something, if you study the same Fishnet type of diagrams and correct the power of the propagator such that all these integrals are conformal integrals, you can go and apply the same techniques and solve for the spectrum exactly in any dimension. But there is something special that happens at even dimensions and not happen at odd dimensions. Remember that in our case for j equal to 2, we got only 2 non-trivial states that correspond to twist equal 2 and 4. It was trace phi square and trace phi box phi. Of course, there is infinite tower of operator with 2 phi 1 scalar, for example, trace phi, 10 boxes and another phi. What about all these states? It turns out that in 4D, all these states are protected. They don't get any loop correction. If you go to odd dimension, they are not protected anymore. They are all talking to each other. So I expect odd dimensions to have an anomaly, kind of, and even dimension not to have an anomaly. Something we plan to work on. Thank you. What do you mean? This is exactly the subject of the talk tomorrow. You know. On the way, no, we did first steps. But the aim of the next talk is how to use integrability in order to compute 3-point functions in this model. Okay. And at the end of the day, we'll express the structure constant there in terms of what is called the quantum spectral curve, the Q functions. This is if you're just interested in the spectrum, this is the most efficient and the best way to compute the spectrum. And the same object are also useful to compute 3-point function. And the aim of the next talk is to take the structure constant and rewrite them in terms of these most convenient variables. So this is why it's so, I think, useful to study such a toy model, because at the end of the day, we will try to understand the structure. We know what is the corresponding Q function for n equal to 4, and we will have to figure out some measure that I'll discuss tomorrow in the way that you fuse them together. This was done in one of paper of Kazakov and collaborator. They construct the Fishnet model for ABGM. It has more funny diagrammatics. But one can, I think, follow the same steps and derive its holograph. Analog steps also. Yes. SYK has the same type of graph for j equal to 2. Exactly the same type. The only difference is that the dimension 1 instead of 4. And correspondingly, all this tower of other operators do not decouple. We find actually for the SYK there is one classical operator that is captured by the fish chain. But there is also all these other quantum operators that become equally spaced at strong coupling and talk to it. Yes. Yes. You are now talking about the space-time theory. Here what you describe is the worldsheet theory. Okay, so when you, for example, when you compute the norm of the worldsheet at a given time of the worldsheet, you have to integrate over all your phase space. Phase space here was all ADS, not a fixed time slice in ADS. This is the space-time theory, not the worldsheet. Christian model is the worldsheet theory. It was tied to single trace operators. Yes. Yes, it's the first quantized string. Yes. The thing about it is that it was integrated over all space-time and not at fixed radial position. I can do it at a fixed radial position, but there I have to include operators with arbitrary number of derivatives, so radial derivatives. Right. So maybe a more abstract way to think about it. What is the basis of a wave function in the sphere? Is some functions that if I give them all, you can tell which operators stand there. And this automatically satisfies this, clearly one-to-one. Right. This is exactly the point of this 1 over n correction. Include this 1 over n correction, this string can, for example, emit a graviton, or can have a 3-point function between the stress tensor or the Lagrangian and 2 of these operators. We'll study one example like that tomorrow, not in the context of holography. But in order to see how it emerges holographically, this is exactly including the vertices, in the interaction vertices in ADS. So far, we have just quantized a single string. Locality here, what locality here means, going back to the starting, it means that the worldsheet theory is local. You have, okay. You see, going to the local, no. It will be a string splitting, but the string to start with is not local in the bulk. It has local dynamics. You haven't done that yet, I haven't tried. Not that this model, we could have stopped in 4D in the bulk, but then we had this crazy model where all the kinetic terms were multiplying together. There was no sense of locality. It was crucial to go to embedding space, realizing this gauge symmetry, which exactly allows us to split the kinetic term, and have something that looks as local as a discrete model can look. This is exactly also made in the map to the boundary, non-local. Every point in the bulk was talking to all the points in the boundary. This is a second quantized picture. It's not the worksheet